All right, so have you ever wondered how we're making those large language models faster,
Hmm.
more efficient,
Yeah.
especially when they're dealing with like massive chunks of text?
Yeah.
Well, that road leads us straight to key value cache management.
Oh.
It's kind of like, um, imagine LLMs are like those super smart but totally forgetful students,
Mhm.
and the KV cache is like their like super organized notebook,
Right.
helping them avoid redoing the same work over and over again.
That's a great analogy. It really highlights why KV cache management is so crucial for
Yeah,
making LLMs efficient.
exactly.
These models they're so powerful,
Right.
but they can be real resource hogs, especially when dealing with those long,
Yeah.
text sequences.
And what's fascinating is that researchers are optimizing these systems on like all these different levels, from
Yeah.
individual words all the way up to the entire computing environment.
Uh-huh.
So we're going to take you on this little journey through three key areas:
Okay.
token level optimization,
Right.
model level
Okay.
optimization,
Mm-hmm.
and then system level optimization.
So we're zooming in from the fine print to the big picture,
Yeah.
like uncovering all the clever tricks that make LLMs work.
Exactly.
Yeah.
So let's start with that most granular level, the tokens,
Oh,
the
yeah.
individual words that make up the text.
Right.
This is token level optimization.
Gotcha.
And at this level, it's all about making sure that the LLM is being smart with its resources,
Right.
keeping the most important information like front and center
Right.
without getting, bogged down in unnecessary calculations.
Yeah.
So the first strategy that we found was this idea of KV cache selection.
Okay.
So imagine a librarian
Uh,
with this magic shelf that can instantly retrieve any book,
right.
but it has limited space, right?
Yeah.
That's our KV cache.
Okay.
We need to decide which books to keep on hand
Yeah.
and which ones to send to the archives.
Right. Right.
So you've got two main approaches here:
Mm-hmm.
static and dynamic selection.
Mm-hmm.
So static is like saying, these books are always going to be popular. It's
Mhm.
just going to stay on the shelf.
Okay.
But dynamic selection, that's more flexible, right?
Right.
Like having that librarian constantly like rearranging the shelf
Yeah.
based on like which books are being requested the most.
Gotcha. Gotcha.
So dynamic sounds a lot more efficient
Definitely.
in the long run.
Yeah.
But what are some of the specific techniques that researchers are using?
Well, one really interesting detail that researchers found is this attention sink effect.
Okay.
Have you ever noticed how sometimes like a first impression can just stick with you,
Oh, yeah.
even if it's not totally accurate?
All the time.
Well, it turns out LLMs can be a bit like that too. They kind of give like way more weight
Yeah.
to the first few words in a sequence.
Interesting.
It's like they just get fixated on that initial input.
So researchers are using this to their advantage.
Exactly. A model called streaming LLM, it actually exploits this attention sink effect to
Yeah.
manage its KV cache more efficiently.
That's so clever.
Yeah, it's all about like understanding those subtle biases in how LLMs process information
Yeah.
and then using that to optimize the whole system.
Right. So managing the books is just one part of the challenge,
Yeah,
though.
yeah.
It's also about, allocating the resources
Yeah.
to handle all those requests.
Absolutely. That brings us to KV cache budget allocation. It's like
Alright.
we're giving the LLM a limited budget and saying, spend wisely.
All right. So how do we make sure those resources are being used effectively?
Well, one approach is to allocate resources like layer-wise.
Okay.
Think of an LM like an onion, right?
Oh, yeah.
It has all these different layers.
Uh-huh.
Each one's processing information in its own way.
Okay.
Some layers might be dealing with like really complex grammatical structures,
Yeah.
while others are focused on like the overall meaning and context of the text.
So it makes sense that some layers would need more memory than others.
Exactly. And then there's headwise allocation, which is even more granular.
Okay.
Within each layer, there are these little units called attention heads,
Right.
and they focus on specific aspects of the text.
So like specialized teams within each department.
Yeah, exactly.
I'm already seeing how this is way more intricate than just throwing a bunch of data at an LLM and hoping for the best.
Oh, yeah, for sure.
Yeah.
It's definitely much more than that.
And one model that uses this headwise allocation really well is Pyramid KV.
Okay.
And it takes this pyramid approach,
Hmm.
so it gives more resources to the lower layers of the LLM,
Right.
the ones dealing with more general information.
So kind of like the base of a pyramid needs to be wider
Yeah,
to support everything above it.
exactly.
Yeah.
So we've talked about selecting which info to keep in the KV cache, how to allocate the budget.
Right.
But what about finding ways to combine information without losing too much detail?
Yeah, that's super valuable for saving space.
Right.
Absolutely. And that's where KV cache merging comes in.
Okay.
It's like organizing your closet and finding ways to combine like similar items into one container
Okay.
without sacrificing functionality.
So we're merging similar pieces of information in the KV cache to save space.
Yeah, exactly. Just like with budget allocation, there are, different levels of merging. You can merge within a single layer, or you can look across multiple layers.
And this is where one of the papers had this detail that really surprised me.
Yeah.
Apparently, sharing KV caches between very different layers doesn't hurt performance as much as you'd think.
It is surprising, isn't it?
Yeah.
Researchers working on this model called KV share,
Right.
they found that sometimes breaking those conventional rules can lead to some interesting results.
Yeah.
So they were actually trying to figure out like which were the most dissimilar layers to share caches between, and it turned out to be pretty effective.
So sometimes a little unconventional thinking can lead to a breakthrough in efficiency.
Sometimes, yeah.
I love that.
It can be good to shake things up.
So let's talk about KV cache quantization.
Okay.
One of the papers used this analogy of like shrinking a high-res photo to share it faster.
Yeah, that's a great way to think about it.
Yeah.
Essentially, we're reducing the precision of the numbers stored in the KV cache, just to save memory. It's like rounding a number to the nearest whole number instead of keeping all the digits after the decimal point.
Right.
You might lose a little bit of precision, but the savings can be, pretty big.
But wouldn't losing precision affect the LLM's accuracy overall?
It can, yeah.
Right.
But the trick is to find that balance.
Okay.
Reduce precision enough to save memory, but without messing with the LLM's ability to do its job.
I see. So that's got to be a delicate balancing act.
Yeah, it is.
But isn't there a risk that we're like oversimplifying things and losing crucial information?
That's a valid concern, and that's why researchers are developing these sophisticated techniques to manage this.
Yeah.
One technique is called KV Quant, and it's specifically designed to handle outliers.
Outliers.
Imagine you have a puzzle where most of the pieces are small, but then you have these few really large pieces.
Yeah.
They don't really fit anywhere.
Okay.
Those are like the outliers in the data.
Gotcha.
KV Quant, it has a way of handling these outliers.
Okay.
So they don't mess up the whole quantization process.
So KV Quant helps to ensure that we're not losing those crucial bits of information just to save little space.
Exactly. It's all about finding those efficient ways to represent information without sacrificing accuracy.
Okay. And then there's KD cache low rank decomposition.
Okay.
Which sounds kind of intimidating.
It might sound complicated, but the core idea is it's to reduce the complexity of the information stored in the KV cache, but without losing its essence.
Okay.
Yeah.
So we're simplifying but retaining the most important parts.
You could say that, yeah.
Okay.
Techniques like singular value decomposition or SVD, they help us identify the underlying structure of the data and then represent it in a more compact form.
Gotcha.
It's like summarizing a really long, detailed report into a concise executive summary,
Right, so you're getting just the key points.
Exactly.
Okay, and I see how that would be really useful, especially when we're dealing with, massive amounts of data.
Right.
What about that technique called Matryoshka KV?
Ah, yes. That one's, it uses a fun analogy.
Yeah, that name really stood out to me.
It's like think of those Russian nesting dolls. Matryoshka dolls. Each doll, it represents a level of compression.
So we're compressing the information in layers, like those nesting dolls.
Yeah, exactly. We start with the largest doll, which has all the original info.
Right.
And then we compress it into a smaller doll, and then an even smaller doll.
Yeah.
And so on.
Wow, that's a clever approach.
Yeah, it's a way to represent the information in a hierarchical and more compact form.
So we've seen how researchers are getting creative with managing individual words in the KD cache.
Right.
But what happens when we when we zoom out a bit and look at the entire LLM architecture.
That takes us to model-level optimization, where researchers are basically redesigning the entire library itself to be more efficient.
So we're talking about actually modifying the LLM's architecture.
Yeah, exactly. Yeah. And one technique that's gaining traction is attention grouping.
Okay.
Remember those attention heads we talked about earlier?
The ones that focus on specific aspects of the text.
Yeah, well, sometimes those heads can end up focusing on really similar things. Yeah. It's like having multiple teams working on the same project,
Right, so it's a bit redundant.
Yeah.
So attention grouping streamlines things by merging those similar attention heads.
Exactly. It's a way to reduce redundancy.
Right.
And make the LLM's processing more efficient. It's like having a really good manager who can see those overlapping responsibilities,
right,
and then reorganize teams to get rid of those inefficiencies.
So that's a win-win, right?
Yeah.
Saving resources and potentially improving performance.
Yeah, exactly.
So how are researchers actually grouping these attention heads?
It's all about analyzing the patterns of attention and identifying clusters of heads that are focusing on similar things in the text.
Okay.
It's like using data analysis to figure out which teams have, overlapping responsibilities and then merge those teams into a more cohesive unit.
So it's a data-driven approach to restructuring the LLM itself.
Yeah.
That's pretty cool. And this is where we came across the idea of lazy layers.
Oh, yeah.
In a model called SimLayer KV. I have to admit, the term lazy layers kind of made me chuckle.
That's a catchy name.
Okay, so what's the story with these lazy layers?
Well, researchers found that some layers are less effective than others when it comes to those long-range connections in the text.
Right.
They're much better at processing local information. So instead of giving them, equal resources, we can optimize the KV cache by giving those layers smaller caches.
Okay, so it's like realizing that some teams don't need access to the entire company archive.
Yeah, exactly.
They can do their job just fine with a smaller, more focused set of information.
Right.
So that leads to significant savings in memory and computation.
Yeah, absolutely.
But attention grouping is just one approach at the model level, right?
Right. Researchers are also exploring different architectures for LLMs.
Hold on. So we're not just tweaking the existing structure. We're talking about completely redesigning the library.
That's right. The transformer architecture has been dominant for a while, but there's a growing interest in exploring, alternative architectures that might be more efficient, especially for certain tasks.
What are some of these alternative architectures?
Well, one of the most intriguing examples is RWKV.
Okay.
This model borrows some elements from recurrent neural networks.
RNNs?
Yeah, or RNNs.
Right.
Which have a different way of processing information than transformers.
I remember reading a bit about RNNs.
Yeah.
They're known for their ability to kind of remember past information.
Exactly. They have this sort of internal memory that lets them keep track of previous inputs, which can be super useful for processing those long sequences of text. And RWKV uses these RNN-like mechanisms to make a more memory efficient approach compared to those traditional transformers.
So it's like streamlining that whole process of remembering past information.
Yeah.
Without needing this massive KV cache to store everything.
That's a great way to put it.
Yeah.
And these alternative architectures are just the tip of the iceberg.
Yeah.
Researchers are constantly pushing the boundaries of what's possible.
Right.
Coming up with new and innovative ways to design LLMs.
It's amazing to think about all these different approaches.
It is.
But so far we've been focused on the LLM itself, right? Whether it's the words or the overall architecture.
Yeah.
What happens when we zoom out even further and consider that entire computing environment?
That brings us to that most expansive level of optimization.
Okay.
System level optimization.
Okay.
Here, it's not just about the LLM.
Right.
It's about the entire ecosystem that it operates in.
So we're talking about the hardware, the software.
Yeah.
All that behind the scenes stuff that most people don't even see.
Exactly. It's about recognizing that LLMs don't exist in isolation.
Yeah.
They rely on this complex web of interactions with various hardware and software components.
And optimizing at this level can lead to some really big gains in efficiency and performance.
Oh, yeah, for sure.
So what are some of the key areas that researchers are focusing on when it comes to system-level optimization?
Well, one of the most crucial aspects is memory management.
Okay.
It's all about finding the most effective ways to organize and allocate memory resources.
Yeah.
So that the LLM has, access to the information it needs when it needs it.
Right. If we're dealing with these massive models and data sets,
Mm-hmm.
memory management has got to be critical.
Absolutely. And one technique that's being used to optimize memory management is paging.
Okay.
Which you might be familiar with from like computer operating systems.
Oh, like how computers swap chunks of data between RAM and the hard drive.
Exactly. And in the world of LLMs, we have this model called VLLM that uses paging to manage the KV cache.
So it's like having a system that intelligently swaps portions of the KV cache between fast and slower memory, depending on how often they're needed.
Exactly. It's all about keeping the most relevant info close at hand,
right,
and moving the less frequently used stuff to the back shelves.
That's a great analogy.
Yeah.
It's like having that librarian who knows exactly which books are going to be in high demand,
right,
and make sure that they're always easily accessible.
Yeah, and it's not just about paging.
Okay.
Researchers are also exploring techniques like prefix-aware memory management models, like chunk attention and memserve.
Mm-hmm.
They take advantage of the fact that many requests to the LLM might share common prefixes.
So like if multiple people are searching for the same phrase on Google.
Exactly.
Yeah.
Instead of storing that same prefix in the KV cache over and over again for each request, these models have ways to deduplicate and share those prefixes, saving both memory and computation time.
It's brilliant.
Yeah, it's like having a shared dictionary of common words so that everyone doesn't have to carry around their own copy.
I love that.
And another crucial aspect of system-level optimization is scheduling, which is all about managing the flow of tasks and ensuring that everything is running smoothly and efficiently.
So we're talking about prioritizing tasks, managing resources, making sure the LLM doesn't get overloaded if it suddenly gets hit with a ton of requests?
Yeah, exactly. It's like having an air traffic controller who directs the flow of planes, to prevent collisions and delays.
Wow.
And there are lots of different approaches to scheduling. Some prioritize fairness, making sure different requests get a fair share of resources, while others focus on minimizing latency, the time it takes to process a request.
And I can see how that would be important in real-world applications.
Yeah.
Where you might have a lot of users all interacting with the LM at the same time.
Right, exactly.
Yeah.
One model that really stands out in this area is Fast Switch. Which focuses on fairness in KV cache management. It has some really ingenious mechanisms for enhancing I/O utilization, minimizing GPU idle time, and eliminating redundant operations.
It's like having a traffic management system that not only directs the flow of vehicles, but makes sure everyone has a smooth and comfortable ride.
That's a great way to put it.
And finally, we have hardware-aware design. Which takes into account the specific hardware that the LLM is running on.
Yeah, so we're moving beyond those general optimization strategies and getting into the nitty-gritty details of how the hardware itself affects performance.
So we're tailoring those strategies to the hardware.
Right.
And are there any specific examples of hardware-aware design that really stand out?
One that really blew our minds is instanfer.
Okay.
This system, it leverages something called computational storage drives.
CSDs?
Yeah, or CSDs.
Wait, the storage device is doing computations. I thought it was just for storing data.
Traditionally, yes, but CSDs are changing the game.
Wow.
Instanfer uses these CSDs to do some of the LLM's calculations directly on the storage device, bypassing those slow data transfer bottlenecks.
So it's like having a delivery truck that can also sort and process packages while it's on its route.
Exactly.
That's amazing.
It's a fantastic example of how hardware-aware design can really push the boundaries of LLM efficiency.
Okay, I need a moment to process all of this.
Yeah.
We've covered so much ground.
I have.
From individual words to entire systems.
Right.
And it's clear that researchers are, leaving no stone unturned in their quest to make LLMs faster, more efficient, and more accessible.
Yeah. It really is remarkable to see all this ingenuity and the collaborative spirit that's driving this field forward. And the best part is, this is still early days. There's so much more to discover and optimize.
It feels like we're witnessing this, technological revolution.
Yeah, yeah.
But I keep thinking, what does all this optimization actually mean for the future of LLMs? Is it just about making things faster, or is there something like deeper going on?
That's a great question.
Yeah.
I think it goes beyond just speed, you know? It's about making these incredibly powerful models more accessible to a wider range of users and applications.
Right.
It's about reducing those computational costs.
Okay.
And the energy footprint of these models.
Yeah.
Making them, you know, more sustainable, environmentally friendly.
So we're not just making them faster, we're making them like better citizens of the digital world.
Exactly.
And as these optimizations make LLMs more efficient, more accessible, we're going to see them integrated into like more and more aspects of our lives.
Yeah.
Imagine a world where LLMs are like seamlessly assisting us with everything from writing and research to education and healthcare.
Yeah, it's pretty amazing to think about.
It is. It's mind-blowing.
Yeah.
This deep dive has been incredible.
It has.
We started with those like tiny building blocks of language, the tokens.
Yeah.
And we've ended up exploring how researchers are optimizing like entire systems to support these massive models.
Yeah, we've seen how optimizing KV cache management is like this multi-dimensional puzzle.
Yeah.
It requires like this deep understanding of linguistics, computer science, even a bit of psychology.
It really does.
Yeah.
And we've only scratched the surface.
Yeah.
I'm already thinking about all the questions that this raises.
Yeah.
Like everything we've talked about has been focused on text-based LLMs. But what about, you know, multimodal LLMs?
Right.
The ones that can process images and videos and audio alongside text.
That's a fantastic question, and it's one that researchers are really grappling with right now.
Yeah.
Multimodal LLMs are like the ultimate multitaskers.
Right.
They're juggling all these different types of data.
So how would KV cache management need to evolve to handle these multimodal models?
Well, for one thing, we'd need new ways to represent and manage all those different types of data within the KV cache. It's not just text tokens anymore.
Right.
We need to account for visual features, audio signals, all sorts of other information.
And the optimization strategies themselves would need to consider how those modalities interact. Right.
Yeah, absolutely.
It's not just about optimizing each one individually, but understanding how they like all work together.
Exactly. It's like designing a transportation system that seamlessly integrates different modes of transport from, you know, cars and trains to bicycles and pedestrians.
It's a complex problem.
Yeah, it's a challenge, but it's also an incredibly exciting area of research.
It sounds like we're just at the beginning of a very long and fascinating journey.
I think so.
Well, dear listener, that concludes our deep dive into LLM acceleration and KV cache management.
Yeah.
We've gone from the tiniest tokens to the vast landscape of system-level optimization.
Right.
And we've seen how researchers are just constantly pushing the boundaries.
Yeah.
It's been a pleasure exploring these cutting-edge innovations with you.
Absolutely. And we hope you've gained a deeper appreciation for this intricate dance between efficiency and power that drives the evolution of LLMs.
As you continue your own explorations in the world of AI, we encourage you to keep in mind that, you know, this quest for efficiency isn't just about speed. It's about making these powerful tools more accessible, more sustainable, and ultimately more beneficial for everyone.
Absolutely.
Until next time, keep diving deep.